So multiplexers. Everybody's fine with a multiplexer, right? Is it easy peasy lemon squeezy or hard or?
It's easy.
Perfect. Okay, now we need to talk about something, and then we'll move to the next component. Imagine the following. You have in your computer something is called what? Power supply, right? And you already have the cable, you put it in you plug it in, and then the computer will be working. When you remove the plug, what will happen? And you don't have a battery. This computer will be turning off, right? How can we do something like that in digital logic? We add something that's called enable. We add something that's called enable. Okay. So enable is what? So for instance, we already defined a device and we call it multiplexer, right? This is our multiplexer. Do you guys remember? And we said the smallest multiplexer is actually have two inputs and one what?
Output.
Exactly. We just add this. Okay. Now, what is the size of this controller will be? How many bits? So here is I0.
1
bit.
This one.
1 bit.
1 bit?
Mm-hmm.
Why 1 bit?
Because there's 1. There's 2.
It might be 1, but why?
Because there's 2. I0 and I1.
Log 2 number of inputs. You're right. I'm just trying to confuse you. So anyway, it's 1 bit.
Yes, we got it right.
Okay. Now, if I would like to add an enable to this circuit, what should I do? I should have a power supply or like something, right? I can, for instance, do here a wire and I call it enable.
Oh, okay.
All right.
Is this still a multiplexer?
It's a multiplexer with enable.
You can add an enable just like that?
I can add enable to anything. I can enable to anything. It's a concept, right? So if this device, I like to control it with enable, I will use it. Somebody will tell me why we have enable. I will tell you why. Because sometimes I don't want this whole entire device to be working. Do you agree?
Mm-hmm.
Then, I will go in a low power.
Oh.
Because, if the device is working 24/7, that will be what? Draining the battery, right?
Yes.
Or draining the source, whatever you call it. It's going to be a battery at the end of the day, right? So you are draining the battery. So let's see how this enable will affect on the device, right?
Mm-hmm.
So we discussed before about, do you remember somebody of you asked me about teaching the order of the inputs and whether it will affect on the circuit implementation or not, right?
Mm-hmm.
And we agreed about it and we are done about this. We'll not discuss it anymore because it's a conceptual thing. Now, if I make a table like this, and this is my truth table, right? So this truth table, it has select location 1 or location 0, whatever. I just have here 1 bit, so it's gonna be just location 0, right? And now I have the P, but there is an extra signal I have in my hand is called enable, right? Where exactly I'm gonna put it, basically gonna be here, enable, right? So this table will be showing me what will be the enable effect with the select for the multiplexer when we will go into the gate level implementation of the device, right? So since I have 2 inputs here, how many states this table will be covering?
4.
4, right? So 1, 2, 3, 4, right? So basically here is 0, 0, 1, 1. And here is 0, 1, 0, 1. Professor, what exactly does enable do? Yeah, so enable is exactly like the power supply. Do you remember the cable of your laptop? If your laptop doesn't have a battery, and you're just plugging your laptop with a power supply into the wall, right? Then the laptop will be working. Do you agree, Alejandro? So imagine that you decided to pull out the cable from the wall while you're doing work, is the laptop will still be working? Exactly. So enable is doing the same thing. So if I would like to keep this component doing work, I will be raising the enable. If I don't want this component to be working, disabling the functionality of it, I will go ahead and do what?
Disable.
Okay, completely saying no. So anyway, we're gonna look into this table and we're gonna actually shrink the table in a fancy way using the element we discussed before and I came up with, is called X. Don't care, right? So anyway, now my enable is equal 0. My enable is equal 0, right? In that case, I don't care that much about my output will be, right? Because I know that, this thing will not be working, right? One of the way to say it is saying that I don't care. Or if you care, that means you are caring and you would like to sit it in a certain location or certain state so that it will not be taking power from you, I can just go ahead and say what? 0. Right?
Mhm.
Everybody aligned with what I'm saying?
Yes.
That's basically exactly like, you are putting your hand in the keyboard while your little brother plug out the cable from the wall and you keep writing, but nothing on the screen because at the end of the day, what? 0.
Mhm.
Same thing, right? Now, when it's 1 and 1, then the multiplexer will do the job, right? So in that
Mhm.
case, if it's 0, so I know I0 will be the output. If it's 1, I know the I1 will be the output.
Oh.
Does it make sense?
Mhm.
So this table can be rewritten in a very nice way, which is basically like this. Enable, select 1, 2, 3. If it's 0, X, it will be 0. If it's 1, 1, 0, 1, it is I0 and I1. That makes sense? Hello?
Yes.
So everybody now understand how I use the X in the context because I already have enable. See, I have enable. So it doesn't matter if X is 1 or 0, it will give me the 0. So that's why it doesn't matter. So I can take this together, combine them, and call them X. So far, so good.
Yep.
Now, I would like to see my implementation, right? So in the implementation, it is straightforward. The old hierarchy of the design, it was like, I have an AND gate like this with I0 and the selects. And then, that select going also with and is I1. And then there is an OR gate. And this is P. Right?
Mhm.
That
Yes.
was our circuit without enable. If I would like to have an enable here, what should I do? Yeah, one of the way to do it is actually to do it like this.
And
You agree?
Mhm.
But is this the only way to do it?
No.
No.
What other ways we can do it? Somebody can tell me.
Can you have I0 and I1 and select an EN?
Exactly. So, the other implementation, which is still valid also, is to have a 3 input AND gate, which is actually 2 consecutive AND gates, 2 inputs, right? So going to be like I0 and enable and select and another and select EN and I1, and then you're going to have the OR gate like this. Right? So if the enable here is 0, here it's gonna be 0, and then you're gonna get 0. If the enable one here happened, then the select will do the job to bring me the output. So this circuit and this circuit doing the same job. But this circuit is a kind of stable, because most of the passes almost look like each other. While this one, there is a very long pass, which is this one, to be a critical pass. And frankly speaking, this is actually working circuit, and then you are disabling it. While from here, I disable the OR gate, and those ANDs will be doing the job. Do you guys agree?
Yeah.
Yes.
Okay, so here and or not gate is doing work, right? And then but the output functionality perfectly fine. I cut it with this AND. But here, when I made this AND, the OR completely is off. So I actually removed some part of the power will be consumed by the OR gate. Sounds good?
Professor, can you please repeat that from the start? I didn't get the first part.
You mean here?
No, not that. Like when you were talking about, no. I mean, when you were talking about like the energy use, like on the last diagram.
This one?
Yes.
Sure. So how many gates in front of you, right? You have an OR, and you have an AND, and you have an AND, right?
Yes.
Now, every single element is contributing into what? The power, right?
Mm-hmm.
So, okay. Now, since I have the enable here, right? When I put them 0, those two ANDs will disable the job of the OR. Do you agree?
Yes.
Because 0 and 0, then this OR will not consume any power, right? So
Yes.
end of the day, this circuit will consume less power than this circuit. Right?
Yes.
Why? Because here, those guys will be still working, but this AND will just disable it.
Mm.
So those guys will be consuming more power than this one. Even both of them doing the same functionality.
Yeah, I see. Thank you.
Make sense?
Yes.
So is it better to have your circuit fully disabled than the top one?
It is better, but it's not better. I mean, it depends on what is your application. So I will give you an example. Have you heard about something called IoT?
Internet of Things?
Exactly. Internet of Things is really little itty bitty tiny devices doing job, right? Like a sensor connected to the door of your refrigerator telling you the eggs are gonna be spoiled in 2 days, go replace it. Or maybe, the cucumber section, it's actually got rotten and you have to replace, and so on. You know what I mean? So you understand my point, right? So end of the day, those elements is doing the job for you to do what? To completely notify you with something. Those devices are very physical constraint, right? So they're gonna be wasting energy really fast.
Energy. Yeah.
Exactly. So like my iWatch here, right? I have to charge it every night. It's really quite annoying, right? But while Fitbit, for instance, I charge it once a week, right? So then this power thing that you have to do all of the power tricks to build the circuit will do the same functionality, but it will consume less power. But on the other hand, have you heard about something called supercomputer?
Yes.
In supercomputers, you already have a million and thousand of the CPU and GPUs and FPGA nodes. And those guys are heavily working, lifting up customers' applications, right? So we don't care that much about how much power will be consumed. We just care about to finish fast.
Oh, okay.
Then, I'm connected into a nuclear power plant. It's just giving me instant powers, right? So who cares? But I need to finish fast. Have you also heard about something called AWS, right?
Yes.
So in AWS, it's an Amazon server. They call it warehouse server that, doing a lot of work, and you submit it to the cloud. Then, I don't care that much about power in this case.
Yes. Okay.
Okay? Makes sense to everybody? Now we're gonna move to our next combinational circuit element, which is called decoder. Before I move to the decoder, maybe I can give you the demultiplexer, because they're similar, right? So let's go to the second one, which is here, DeMUX. So in the DeMUX, exactly like while you are driving your car, you are going in one way, and one day, like while you are driving in the highway, you find yourself, you can go into what? 2 ways. So you are in one lane, and then this lane got doubled. So you have now choices. You should go in this way or that way, right? So it depends on what your GPS, or it depends on your final destination. Do you agree? So the demultiplexer are doing the same thing. Somebody will tell me why we are actually learning about demultiplexer, because it's also used for routing. What is routing? Again, if you guys not following, do you remember your digital logic lab? While you are doing the work, you already have a bunch of wires, right? And you try to connect from this pin to this pin. That's called routing. Okay? So demultiplexer, it's the reverse of multiplexer. So you already have here.
So you take one input, two
one
outputs.
Input and two or more. Okay? You're gonna see something which is really fun. It's almost multiplexer. But multiplexer losing OR. You will see how. So now we already have here an input, and you already have a P0 and you have P1. Right?
Yeah.
Then who gonna help me to take a decision? A controller. Do you agree? So here is 0 and 1, and I have here a selector. So imagine this is actually P to N minus 1. So there is an N outputs. In this case, the selector will be log to number of what outputs. So frankly speaking, if I move into the 1x2, so basically it's called DeMUX 1x2 or DeMUX 1xn. So before it was nx1, right? Now it's 1xn, right? Because I have one input, multiple outputs. So example, DeMUX 1x2. If I look to 1x2, I would just make it like that. By the way, be sure that you are using the same notation I'm using. I know that you guys also look into the internet, which is fine, but while we are in exams, use notations. Same notation that we are following in the course material and the classes. So you already have here 0 and 1, and here's the input. If you are drawing to me demultiplexer, you're gonna draw it like that. If you gotta draw to me what's called multiplexers, you're gonna draw it exactly like that. Anyway, back to the circuit. So I have here one input, and I have two outputs, which is P0 and P1. And I have here the selector gonna be what? 1 bit, and I will call it select. So in that case, I have a truth table, select, and in this select, it can be 0 and it can be 1. How many outputs I have? I have here P0 and I have P1, right? Mm-hmm. If select is equal 0, so I'm guaranteeing that, P0 will be I, while, P1, I have no idea. You can make it, I have no idea, or you can make it what? 0. It's up to you. So here, I'm gonna make it 0. Sounds good? Mm-hmm. While in 1, P0, I can make it, I have no idea, or I can make it equal what? 0. So 0, and then, P1 will be I. I. In that case, circuit-wise is very straightforward, right? Why? Because, I have here I, right? Here is an I, and here is what? Select.
Is this not a XOR? XOR? Huh? XOR?
No, I'm going to show you. It's not XOR because you already have two outputs. So this one is something, this one is something. Look, I will show you. So now, I have here the color of the redness here going to be like that. And I'm gonna go with what? With the inversion of the select, and they're gonna be my what? My P0. While if I take the different color like this, and I take this color like that, and I say this is my what? So have you noticed this circuit look like what? It is a multiplexer without an OR gate. Do you agree?
Mm-hmm.
Makes sense to everybody? Now, if I want to add an element like an enable connected to this demultiplexer, it's gonna be almost the same like the old design we made here, right? So you're gonna have like an AND I enable and the conversion of the select, and I enable, and they're gonna be P0 and P1. And they're gonna be what? DeMUX 1x2 with enable, right, gate level implementation. So far so good to everybody. If you have any question, feel free, stop me, and I will actually revise and go back. Go ahead.
There should be a select in the middle, right?
Yeah, you forgot the wire for select.
Oh, I forgot. It's just select. Thank you. Okay. Any other questions? Any other concern? Excuse me. Okay. Now we gotta move into what? We are going to move into the network of demultiplexers, right?
Oh, never mind.
So what about if I would like to make 1x4 from 1x2?
Same thing.
Gonna be also network 2 power. Do you remember the 2 power 0, 2 power 1, 2 power 2 stuff? We're gonna flip it. So gonna be here 2 power 0, 2 power 1, 2 power 2, bum, 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 right? So how? Here is actually 2 power 0 is 1 demultiplexer. And this is my I. And here is a selector. Then the second one 2 power 1. So that means 2 demultiplexers. So 2 demultiplexer. P0, P1, P2, P3, and those guys will be common select. So this select 1 and this select 0, and then you will be able to what? This circuit with 3 DeMUX 1x2, I can build the equivalency of what? DeMUX 1x4. Same thing as we did with what? The multiplexers. Any question? If there is no,
The P0 is not flipped like the multiplexer though, right? It's not P0, P2, right? Remember how we did for the inputs, we did
the ordering, it's up to you, right? You can make here 1, you can make 0. You can see how can you make that arrangement. But the concept of the connectivity, you have to have a demultiplexer, and that will be branching into demultiplexer and so on.
Gotcha.
Make sense? Okay. So if there is any question about this, so I can say that we finish multiplexer, demultiplexer. So you can try to make any connectivity between of them. Like you can come and say that I have a multiplexer, right? Look. And then I will connect it to demultiplexer. Right? Now I made the most simple routing I can ever make, right? So here is I0, here is I1, here is P0, and here is P1, and here I have a select 1 maybe, and I have here a select 0. I can make it like that, right? 0, 1, 0, 1. All right?
Wait.
Huh?
So
Sorry.
just like a pass through.
What is this?
I mean,
Oh,
just
no.
I'm trying now to put pieces, right? Because what do I mean by increasing the abstraction? That means I'm not gonna build everything with Git level, right? I'm gonna build it with devices. Do you agree?
Oh, yes.
So I'm showing you now. I'm bringing device with device, connect them together. What will happen? Just trying here, right?
So I0 will go to P1, I1 will go to P0.
Or vice versa.
Well, I guess it could be depending on the select, right?
It depends on the select, exactly. You can, one of them can be I0, one of them can be I1, one of them can be nothing, the other one will be nothing. Both can have the same thing. It depends on the combination of these two guys, right?
Oh. Okay.
Yeah, so if the select was 0, 0, then it'll be I0 will equal P0. If it's
Exactly.
1, 1, then it'll be I1 equals P.
Exactly. But by this way, you increase the chances of controlling multiple ways, right?
Mm-hmm.
That makes sense?
Yep.
You can even make it even worse, if you want, can just make it like that, All right?
Mhm.
Make sense?
Yep.
Anyway, now we're gonna move to our third important combinational circuit component, which is called decoder. Decoder. So the decoder, following the same footsteps that we already made with the rest of the stuff, right? If I have a decoder like this, here's my decoder, right? The decoder is basically number of inputs x to power number of inputs. And you call it like this decoder. So here is I, here is 2 power I. Somebody's okay.
Wait, is that say decode number I times 2? Or what is that?
This
X?
is number of inputs, and here is
Yeah,
2
is that-
power number of inputs.
So what is the X in the middle? Is that times?
It's like, no, it's not time. It's like this. Do you remember when I made the multiplexer? It was 2x1, 1x2.
Oh,
time,
okay,
right?
okay.
This x is like, this something to separate between input outputs, basically.
Gotcha.
Okay. So now let's make a more specific example, right? So if I have decoder 2x gonna be what? 2 power 2, 4. Right? 2x4. So that means, I have a box like this, and it has S0, S1, that means 2. And I have 4 outputs that gonna be D0, D1, D2, and D3. And inside the box, I will write 2x4 like this, and this is the code. So from this information, I draw the circuits in abstraction level of the decoder, right? How is this decoder works? It's basically, it's a decoder, right? And the decoder that, I'm trying to specify based on encoding information, what line will be on. Okay, so the truth table describing the decoder is the following. So how many inputs I have here? I have S1 and S0. Do you agree? How many outputs I have here? I have D0, D1, D2, and D3, right?
Yeah.
How many states this table will be covering?
8?
Why? 4.
Sorry, 4.
The states determined by the number of inputs. Do you agree?
Mm-hmm.
It's gonna be here 1, 2, 3, 4. 0, 1, 0, 1, 0011. Now, let's see how the decoder mechanism work. So if I see M here, M0, M1, M2, M3, right? So if I see 0, it means that, you know, the line D0 will be active. When I say active, it has to be active high or low. Wait, I didn't tell you. There is something that's called active
Oh, my bad.
high, active low. Active high, active low. Active high, that means 1, as you said. But if my circuit is active low, so that means it's going to be what? 0. And that 0 will be doing the same job of 1. So it can be active high, active low. You know, they write it high or H, and 0 we're going to write like low. If you open the tutorial, not tutorial, the manual of one of those, your IC is basically TTL, right? You will find in the table sometimes they write HLL, HLL, and so on, right? That means active high, active low, active high, active low. Open one of the ICs that you are using for the 2300 lab, you will find. Okay, so here, you know, if I want to write it with active high, like a symbolic, I will write here H, low, low, low. Here, low, H, low, low. Here, low, low, H, low. Here, low, 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 H. Okay, so what does it mean? That mean can be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. In the case of the active high. Because this decoder will give me a multiple lines, right? So when I say 0, that means I'm talking about path 0. When I say 1, that means path 1. When I say 2, that means path 2 and path 3. And then, you know, I will start branching. Okay? Okay, Duke?
Yep.
Okay. Now we're going to look into the circuit level of the little itty bitty 2-4, right? Let's see the 2-4, how it look like. So in the 2-4, as I can see this table, the implementation is very straightforward. D0, it has one min term on and the rest are off, right? So I can actually write like this, D0 as a function of S1 and S0 is equal to M0. D1 as a function of S1 and S0 is M1. D2 as a function of S1, S0 is M2. D3 as a function of S1 is 0 is equal to M3. Right? Implementation. You can actually make it in a fancy way. You can just go ahead and just do it like this. Here's my S1, and here is the reverse of it, right? And then, you know, you can come here and say S0, and here is the invert of it, right? So now we're gonna use different colors. So I can just go ahead and, you know, 0, 0, right? So 0, 0, that will be D0, right? And then, you know, the second is gonna be S1, right? So gonna be here like this, and I'm gonna be 1 here. D1. Then, you know, the reverse. So gonna be the reverse. So I take this. D2. Then I take the other color. So it's gonna be 1 is 1, 1, right? So D3. So pretty much if you have a circuit like this, you can just make a box like this, and inside this box will be this AND, and you know S1 and S0 is the input, and those guys gonna be the output, and the gate level implementation will be that. So far, so good.
Mhm.
Okay, what is the longest pass we have now?
T3.
I have no idea. I mean, what is the longest pass and what is the weight of it in terms of the response time? So the response time is gonna be something like this. This is the longest one. Anything involving the NOT gate with AND, right? Whatever you can see. And they're gonna be what? NOT gate followed by AND gate. And then you will see the timing from the manual, and based on that you will say this decoders will take this amount of time to produce an output.
Oh, okay.
Make sense?
Mm-hmm.
What type of questions I can ask in this particular problem implemented using NAND gates? What you gonna do? You're gonna convert every single NOT gate using NAND gates. You're gonna convert every single AND gate with NAND gate, and the circuit will be using NAND gates, right?
Mm-hmm.
What about if I tell you go ahead and implement it using NOR gates? You're gonna do the same thing. What about if I ask you with a specific gates, you know the equivalency and how to change from one to the others, and you can just do the implementation. Sounds good? Now, if I like to add to the decoder enable, what will happen? So here is my decoder, and here is my input, which let's call it S. And here gonna be the D1, 2, 3, 4. D0, D1, D2, D3, and D4. And that's actually 2 by 4. And here's decoder. And I have here an enable.
Wait, I think.
Hmm?
Don't you have too many?
What
You
happened?
have 5. You have 5, right?
I have an extra one. You're right. So basically, that can be taken away. Do you agree? Okay.
Mm-hmm.
If I see the circuit like this, so that's called what? Decoder 2 by 4 with active high enable. This is 2 by 4 and active high enable, because see the wire is completely coming like in a straightforward. If you want to add in the simple active low, look at this. So you're gonna make the same circuit like this, and here is the S, and D1, D0, D1, D2, D3, as you said, D0, D1, D2, D3, and then I will make a circle like that, and then I go like this. That's gonna be active low. So I'm gonna write it to you. So gonna be 2, 4, decode, and here we're gonna be active low enable for the decoder 2, 4. This thing is telling me there is a negation happening. Okay? Any questions so far? Before we will move to the truth table involving the enable.
So what's telling you the negation? The circle?
Do you see the circuit?
Oh, that, okay.
That means, you know, this thing will work when the enable equals 0.
Okay.
Oh,
Here, this circuit will work when this enable is high, 1. Okay?
mm-hmm.
Okay. Now we're going to start with truth table for the decoder with enable. So if I look at it very carefully, how many inputs I have, it's going to be the enable and S, right? And since we are talking about 2 by 4, so that means this S is going to be S1 and S0, right? So here we're going to be enable and S1 and S0. And how many outputs I have? I have the D0, D1, D2, D3, right?
Mm.
This table will be covering how many states?
Eight.
8.
I still want to say 4.
I'm gonna say 5, which is 8. You know, all of you are correct. You know why? Look, this state, when enable is 0, I don't care about what those guys are.
Yeah.
Then I still have 4 after that, right? So which is gonna be 1, 2, 3, 4. So gonna be 1, 2, 3, 4, and they're gonna be 0, 0, right?
Mhm.
In this particular states, which is 4 states actually, those 4 guys, you know, D0 and D1 and D2, D3, it depends on what do you want as a designer, right? If you are seeking low power, make it 0, right?
Mhm.
Somebody else will tell me, you know, but in some circuits, if I put it X, it will be low power. You know why? Because then K-map will do what? Will make more optimization, then less resources will be used.
Mhm.
Okay? Sounds good?
Yeah.
Now, if 1 here, then you're going to be 1, 0, 1. Then, you know, 0, 0, 1, 0, 0, 0, 0, and 1. And that will be exactly as we discussed before. So now we learn how it works for a small decoders. We learn what is enabled and how it works. Now we're going to learn something new, which is called what? How can we build an array or network of the bigger small decoders to build a bigger decoders?
Oh.
Okay. So also, you know, if I say that there is a decoder 1x2, what does it mean? It means that you already have a single input like this, S, and then, you know, D0 and D1, right? 1x2 decoder. All right. And then you're going to do the same thing, you know, if it's S01, then, you know, D0, D1, you're going to be here 1, 0, here going to be 0, 1. Right? Sounds good?
Yep.
Now, I would like to build 3/8 decoder using 2 4 decoders. 3/8 decoders using 2 4 decoders, right? So how can you do this? That's a very straightforward problem to solve. Period. You know why? Because the following. How many outputs here we can have?
8.
8. How many outputs I have here?
4.
So I need how many?
Another 4.
I need 2. So I need here, like, you know, like this, 1, 2, 3, 4. And that will be D0, D1, D2, D3. And then I need another one here, gonna be what? D0, D1, D2, D3. Right? But since, you know, I want 8, so I can actually rename those to be what? 4, 5, 6, and 7. Right?
Mhm.
Now, so now I use 2, 4, and 2, 4. In this particular case, I have here S0, S1, and I have here S0, S1. But decoder, when it has an 8 output, it has a 3 inputs. Do you agree?
Mhm.
In this case, what we can do, we can actually take a wiring and connect it like that, and take another wire and connect it like that, and then, you know, I can remove those and just make it like this. And then I don't need this and this. But still I have 2 wires. Do you guys agree?
Mm-hmm.
I need the 3rd wire. Where is my 3rd wire? It will be the enable.
Oh.
So in that case, I need here enable, and I need this enable. So that means this decoder has to come with enable, right? And in that case, I can just come here and flip like that and connect like this, and they're gonna be my S2. Let's test it, right? If I go ahead and make S2, S1, S0 like this, right? Then, you know, I have here D0, D1, D2, D3, D4, D5, D6, D7, right? How many I should have? 8, right? 2, 3, 4, 5, 6, 7, 8. The good thing I'm gonna do here, 1, 2, 3, 4. 1, 2, 3, 4, right? Look at this. When S2 is equal 0, what will happen? That 0 will go to this NOT gate and it turn what? 1, right? While this 0 will be here, right? So it's telling me this guy will be disabled while this guy will be what? Enable. Then, you know, the S0, S1 will be connected actively in this while it's doing nothing here, right? Then, you know, if you write here 0, 0, you know, 0, 1, 1, 0, 1, 1, that will be covering 1, 2, 3, 4, 0, 1, 2, 3, 0, 0, 1, 0, 0, 0, 0, 1. Right? Everybody agrees with me? Somebody will come and tell me, but what happened with those, right? Since, you know, this enable is 0, and from the table that we discussed before here, right, with the enable, zeros came here, right? Look. So I'm pretty much confident I can make those guys like a 0. Now, when 1 happened in S2, so if I go ahead and, you know, remove this 0 and I put here 1, what will happen? That 1 will go to the NOT gate, it will tend to be 0, and that 1 will be here. So who gonna be disabled? This will be enabled, and this guy will be what? Disabled. Then the S0 and S1 will be moving to control the second one, while the first one will be what? Disactivated. So let's translate this. The first one is disactivated. It's going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? And here I have 0, 0, 0, 1, 1, 0, 1, 1. So let's look at it. So end of the day, you know, this particular part is controlling this part. So going to be what? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. End of the day, the behavior got the same continuation if you just have one what component. Any question?
So you put that inverter there so that one of them would go out or be disabled at one point?
Exactly. Because, you know, if you make both of them work at the same time, it will be a mess, right?
Yeah.
So
Correct.
would this be considered as a max term?
As what?
A max term?
Yeah, it's still gonna no, it's still min terms. You're using min terms here, right? M0, M1, M2, 7, right?
But isn't the output become a max term because it's 1 and 0?
Max term and min term, they're vice versa, right? So I can make here min term and max term. When you say max term, that means you're looking for any zeros will cause the whole function to be flipped to 1. When you say min term, you're looking for any ones will make the function equal 1. You know what I mean?
Yeah, okay.
It's completely different. Don't mix, you know?
So if we didn't have an inverter on there, then the second decoder would just be switched, right?
So think about it. If there is no NOT gate here, you know what will happen? It will happen that, this table, did you see this part? It'll be replicated here as well. And then, those two guys will be zeros, right?
Correct.
Oh, okay. Yeah.
Sounds good?
Yep.
Okay, so we can stop here for today and we can discuss more next time. Do you guys have any questions? Is everything straightforward?
Mm-hmm.
Yep.
Okay, so it was my pleasure to talk to you today. Keep in touch, and if you have any problem, just let me know and I will be more than happy to assist you. Remember that, we're gonna have the coming Wednesday, the first midterm. So I will be discussing to you on Monday, the coming Monday, the instructions, how we're gonna work and all of these things. If you guys remember from the syllabus, the midterm will be taking the time of the 8 o'clock in the morning till midnight. On Wednesday, we will not have a lecture because, I will allow you guys also, if you like, to use the time of the lecture to answer the midterm. Make sense?
Okay. Yep.
Okay. So God bless you guys and stay safe and see you on Monday. Have a
Have a
nice
good one,
weekend.
Professor.
Thank you.
You too.
Thank you.
Professor.
Bye-bye.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you.
Professor,
Yes.
are we gonna have class the day of the exam?
Huh?
Are we gonna have class the day of the exam?
I'm gonna have what?
Are we gonna have class?
No. I said no.
No. Okay.
Okay.
Thank you.
Thank you. Bye-bye.